Good morning, folks. This is Todd Coburn with your Aerospace Structures series. This lecture is on statics of particles, specifically when we're dealing with forces in 3D. This is an extension of our last lecture where we dealt with forces in 2D. The key to evaluating forces in 3 dimensions lies with the direction cosines for many problems. Understanding how this works can make the analysis fairly straightforward to dispatch. We're going to start off looking at a force in 3 space. What that means is we're talking about 1 space. We're talking about a force that's something that moves only in one direction. 2 space would be a planar problem where the coordinates can be defined by a single plane. 3 space, when we have a 3-dimensional coordinate space system, which means 3 dimensions, and we're going to get all 3. We're going to need all 3 coordinates to identify where a point is, and therefore where the endpoints of a vector are. If we're dealing with a force in 3 space, we have a vector, and it's oriented in 3 dimensions. Now, the first thing we're going to need to do is identify what our coordinate system is. We can use any right-hand rule coordinate system, but it is important that we define it. Once we define that coordinate system, you'll find it's, when we look at this coordinate system, you'll notice that it's not easy to figure out what direction this vector is going based on just that coordinate system. So it's convenient to often move our coordinate frame so that it aligns with the endpoints of the vector. What that means is we're going to take the XY plane, we're going to place it through the nose of the vector and through the toes of the vector. We're going to take the XZ plane and move it through the nose and the toes. And we're going to take the YZ plane and place it through the toes and the nose. And when we're done, we're going to end up with a 3-dimensional box in which our vector is included. That makes it easier to visualize what the orientation of that vector is. Now that we have this box, we can see that this particular vector is moving from the forward left corner or the near left corner to the far right corner. Now, the next thing we're going to need to do is identify any 2 points along the vector. Anytime we're dealing with a line segment, say a cable or a string or a rope that's carrying load like tension load, then we will need to use the direction of that rope in order to define the orientation of the vector. Remember, a vector has magnitude and direction, and the direction is an important piece of solving the problem. And we can use any 2 points. Certainly we can use the endpoints of the vector as we see here. We see point 1, the toe of the vector is at point 1 with coordinates x1, y1, z1, and the nose of the vector is at point 2, which is at x2, y2, z2. We can use these endpoints to define the orientation of this vector by subtracting the first from the second node, which means if this segment is going from point 1 to 2, we would take the point 2 coordinates and subtract the point 1 coordinates. And we're going to use this to define the direction cosine, which is everything we're going to need to define a unit vector along that line of action, which then completes our analysis of that particular vector. That gives us all we need to know about the direction. We can just add magnitude to it, and we've got everything, the whole enchilada. Now, while we're showing the endpoints here, it's important to note that we actually don't have to use the endpoints. We can use any 2 points along the vector. So anytime we have a line segment that we need to identify, or a vector, a force vector, we can use any 2 points along that vector. Often there are some points that are more convenient to define than others. And we can use any 2 convenient points as long as they're not coincident or at the same location. The way we're going to do this is we're going to use the distances between these 2 endpoints, which means we're going to take x2 minus x1, and that's going to give us dx, or the change of position along the x. We're going to take y2 minus y1, and that gives us this position dy, and we're going to take the z2 minus z1, and that's going to give us this position dz. Now you'll notice something here. You'll notice that while these are three scalars, they actually have direction. Since dx is from 1 to 2, and we found it by subtracting 2 minus 1, that means what that actually is, dx is actually a vector oriented like this. dy is actually a vector oriented like this, and dz is actually a vector oriented like that. You see that? So while these are scalar distances, they also have direction because we said this, we're defining this going from point 1 to point 2. Therefore, we're taking x2 minus x1, y2 minus y1, z2 minus z2, minus z1, and this enables us to completely define the direction of this vector. So we can write this out like this. Now, in order to find the magnitude of the length from point 1 to point 2, we can just take the sum of the root mean squares, which means dx squared plus dy squared plus dz squared, square root of all that. That's the distance from point 1 to point 2. Now, we can define the unit vector. The unit vector is actually what we're after. And the unit vector, remember a unit vector is a little vector of magnitude 1 moving in the same exact direction. And we often use the symbol lambda, and it's a vector. And we can say then that the unit vector is moving in the dx direction. That's how much it totally moves. If we did this, dxi plus, that means the dx component in the x direction. Remember that coordinate, that unit vector I, j, k is a little vector that each one has a length of 1 unit so that we can use that as an operation without modifying our system. So what we have here is this distance. The distance from 1 to 2 is actually dxi plus dyj plus dzk. That's actually the full distance going dxi plus dy in the j plus dz in the k, and that perfectly defines our vector. Now what we're looking for is not that vector itself, but the unit vector, which means if we will get a little unit vector of length 1 if we now divide that by its total length. So if we take d divided by the total length d, that will give us this unit vector that we were looking for, which means dx over d in the I plus dy over d in the j plus dz over d in the k, and that is our little unit vector. Now the force, the vector force F, is defined as the magnitude, the scalar value of the magnitude of the force times that unit vector, and that is the complete definition of the vector, magnitude and direction. And what we end up with is that will give us whatever is here, fx in the I plus fy in the j plus fz in the k. Now it's important to note I'm showing all these as positives, but actually these can be positive or negative. In this case, our z component will be negative, and there will be a negative sign. Even though this is positive, this component here would be actually negative. So those are the fundamental building blocks that we're going to need to use. So we first identify what our points are. What that means, let me back up again. Let's just say we have, let's say we have a flagpole, and we tie it down, and it's located here at some point O, and we have a rope that's attached here, and let's say there's some kind of force on this thing. This rope is going to go into tension. If this is point A and this is point B, then actually this is going to be in tension. We can draw a free body diagram of this point A, and we'd have this force applied here. And now we have this cable in tension. We'll call it T. And that tension is moving from A to B, and it's a vector. All we have to do is identify the location of the coordinate system. Let's say this is 5 inches, and this is 20 inches. And let's say this is all in a plane. What that would mean is this vector, when we move from here to here, B is going to be at 5, 0, 0. At A is going to be at 0, 20, 0. And therefore, the line segment AB is simply B minus A, which is 5 minus 0. In the I, it's 0 minus 20 in the J, and it is 0 minus 0 in the K. That's our line segment. That's how we do this, and we can actually use any points along that in order to do that calculation. So this seems a little trivial, but this is the key to solving it, the first key. So our force then is that unit vector. It's F times that unit vector, which was dx over d, dy over d, dz over d. Now the direction cosines are another tool that we're going to use, and they're defined as the cosine of each angle. The angle that this vector F makes with the coordinate axes. So the angle that this vector makes with the x-axis. So what we're going to do is we're going to look here and say, okay, moving from the toe of this vector, we actually have x, y, and z, right? Therefore, what this says is the angle that this vector makes with the x-axis, that's what we're going to call theta x. So it's the angle that the vector makes with the coordinate axes, the positive coordinate axes. So from that vector to the y-axis, this one is theta y, and the vector that this makes with the positive z, this angle here, is theta z. We can calculate that by just taking the cosine of theta x is just dx over d. The cosine of theta y is just dy over d. The cosine of theta z is just dz over d. And that is another way of specifying the unit vector, because this dx over d is the unit component in the x direction and so on. Got that? So what this means is the vector force can be also written this way using those direction cosines instead of using the dx over d's. Often for our purposes, using dx over d, dy over d, dz over d will be more efficient. However, the direction cosines are sometimes key to using that. We defined our unit vector as dx over d. We could also define it using the direction cosines in this manner. And that's what our little unit vector looks like. Make sense? And it's also important to note that this direction cosines, the sum of the direction cosines squareds, actually has a value, a magnitude of 1. By definition, that's how we set it up. Okay? So this is one key principle. We're going to see how this plays out and how we use it to solve problems in a few minutes after we study this a bit more. So we define the direction cosines as our 3 angles. This is the angle that this is a different vector, but this angle, if we take the force and we find the angle that it makes with the x-axis, right? That's this angle here. That's our theta x. And the angle that it makes with the y-axis, that's our theta y. And the angle that it makes with the z-axis, that's our theta z. Once again, that is the direction cosines. Okay? We said that. And now we also said that we can actually look at this also now, since our total force is, this is our unit vector. Since our total force can be written like this, F equals, we said it can be the direction cosines, or that F times lambda, right? Another way to write it is the magnitude in the x in the I plus the magnitude in the y in the j plus the magnitude in the z in the k. That is another way to write it. And this fx is just f cosine theta. Fy is just f sine theta, which is the same as f dx over d, f dy over d, and so on. Got it? Okay. Those are the building blocks we're going to use. We're going to use this all through statics. We're going to use it next semester when we get into dynamics as well. And you're going to see it for any kind of engineering, orbital mechanics, and other things where you're dealing with free space. This is another look at the same thing. We're seeing once again a vector f, and we see how the theta x, the theta y, and the theta z are defined. How the coordinates f of x are defined, how the total vector f is defined, how we can write it either as components fx, fy, fz in the ijk, or as using the direction cosines, cosine of theta x, cosine of theta y, cosine of theta z, or using the unit vector f times lambda. This needs to become like your second language, like addition and multiplication are to you. In engineering, we're going to need to use this a lot, particularly in statics and later on in orbital mechanics. Okay, we said all this. All right. So we said this already, but this is a reminder that the easiest way to specify many three-space vectors is by finding any 2 points along the vector. They do not have to be the endpoints. Any 2 convenient points along the line of action can be used, and then we're going to choose the direction. Now, often we'll know the direction, like in this case. Other times we won't. Then we'll just specify a direction. And if after our analysis we find out that the magnitude is negative, that means that that direction is the opposite of what we assumed. So we're going to use any 2 points. We're going to calculate our dx, dy, dz as the difference between those points. Calculate our direction cosines accordingly. Got it? All right. So we've been talking about using the coordinates of the any two points along the vector to specify the vector in its entirety. Another tool that we will run into is when we project a vector onto another plane. So sometimes we can just take the coordinates and use those. Other times it will be more convenient to project our vector onto one plane and then use that projection to project it onto the other 2 coordinate axes. Here's how that works. Let's say we have a vector f in 3 space. And what we want to do is first, in this case, project it down onto a horizontal plane. This means the xz plane. So remember, we can just drop, if we're going to project it down on the plane, then we're going to take something, since we're projecting it onto the horizontal plane, that means we're going to come down parallel to the y-axis. So we drop a line parallel to the y-axis until it intersects the plane, and that will give us a projection into this xz plane shown here. Then we can take a line parallel to that from the nose. That was from the tail of the vector from the nose, and now we have a little box. We'll see that this projection, we're going to get this component, which we can say call f horizontal, since we're projecting it onto a horizontal plane. And the other component is this, which is actually just our fy. So we projected this onto the horizontal plane and onto the vertical axis. We then are going to, so this is perpendicular here, right? And this is perpendicular, and this is perpendicular. Then what we can do is take this projection FH, and we can project it, which means we're going to take a line parallel to Z and put it here, take a line parallel to X and put it here. This is perpendicular, and this is perpendicular. This gives us the other 2 components. This gives us the Z component, and it gives us the X component, or we can draw them here and here. It's a little more convenient. This is now Fx, this is now Fz, and this was Fy. So what we did there is we had this point, this vector, we had the x and the y, and we had the z. We first projected it down onto the horizontal plane, FH, and projected it onto the y, Fy. We then took the projection and projected that onto Fx, and we projected it onto Fz to get our 3Fx, Fy, Fz. F equals the magnitude F times that lambda, which is Fxi plus Fyj plus Fzk. Let's lay that out. We'll let the slide run its course. So we projected this onto the horizontal plane. That gives us the projection, Fh and Fy. We then project that Fh, that horizontal projection. Oh, this is drawing attention to the idea that we can use the direction cosine with the y in order to do that, right? What this means is Fy is just F cosine of theta, y, right? And Fh is actually F sine of theta, right? That's the same. Fh, that's the same as the Fh down here. It's the F sine of theta y. Got it? Then we now project that horizontal onto our two axes. Now these are poorly drawn and don't look like they're parallel, but they are. And that gives us our other two components that we talked about. They cause some other angle with the axis, right? This is not the direction cosine. This is just another angle phi. This is drawing attention to this as well. We see once again we have this F, which makes an angle with the vertical and is projected onto the horizontal plane. We then use that projection to find the other two components. So our Fy is F cosine of theta y, Fh is F sine of theta y. Fx then is that horizontal component times the cosine of that phi, which is actually, since Fh is this quantity, we can write it this way, and Fz once again can be written like this. Got it? Okay. So in our first example, we're going to keep it pretty simple. We're going to focus on this force P. Let's say that it's 500 pounds, and let's say that we want the X, Y, and Z components. The easiest way with the information that we're given, and the way we determine whether we're going to use 2 points on the vector or this projection followed by another projection, is really what information we're given in the problem. In this particular case, we can see we've been given some angles. We see we already have the direction cosine with the theta with the y-axis. So we can actually use that to calculate the horizontal component directly and then project that onto the two other axes. So we're going to take 500 cosine of 40. That 500 cosine of 40. What we're doing first is we're getting the projection. So we're going to take the x component is going to be the horizontal component, which is P, right? P sine of 40. That is this component, which is the same as this component, which we can call pH. Then we take that pH and we project it onto the x, which is pH cosine of 30 degrees. So this is pH cosine of 30. That gives us the magnitude of the x, px. In this case, we're calling it fs, right? And then we can take that and we can say, okay, that same projection times this, the sine of this 30 degrees, and that will give us our other, as we're going to see momentarily here. Let me clean this slide up and we'll look at that. So having done that, we now say, all right, for the vertical, we can calculate at the same time 500 cosine of 40, and then we have our z, which is once again going back to the horizontal projection, which is this guy, followed by, multiply that by sine of theta. So sine of phi, which actually is, we did first the cosine of phi for this projection, and then we do the sine of phi, which is the same as this guy, when we draw a line parallel to here. And that gives us our FZ, which is right here and right here. Make sense? So that's how we can use projections to define those coordinates. Once we have those components, Fx, Fy, Fz, we then can calculate the total magnitude, the sum of the root mean squared, except that we already know that it's 500 pounds. And we can define the direction cosines. Cosine of theta x is Fx over F, Fy over F, Fz over F, as you see here. That's all there is to it. Now, many of our problems will be a little more challenging than that. Let's go ahead and look at some examples there. This is actually quite similar to our last one. Here we have a little pole that's restrained by some wires, and we're going to focus on one of the wires for this particular problem. And once again, we're just going to look, we're going to focus on this guy wire from A to B. We know that the tension is 2,500 newtons, and we're just going to try and calculate the components and then the direction cosines. Now, in this particular case, we see we've already been given the location of the endpoints. What this means is the easiest way to do this is just to solve using those 2 points along the wire. And we know where this point is, we know where this point is, so that will be the easiest way to solve it. We know the tension, and we're looking for the force acting on bolt A. The force acting on bolt A. What that means is we're going to focus on point A, and we're going to try and calculate what this tension vector is. In order to do that, what we're doing is we're moving from point A to point B, right? What that means is we're going to need the coordinate of point A, which is at, it looks like 40 meters, and in the X, and 0 meters in the Y, and negative 30 meters in the Z. Point B is at 0 in the X, 80 in the Y, and 0 in the Z. So our segment AB is going to be 40 from B minus A, right? So 0 minus 40 in the X, which is I, plus, and then we've got B minus A, which is 80 minus 0 in the J, plus 0 minus negative 30 in the K. That means we're negative 40I plus 80J minus 30K. If we look at this, that's AB. If we look at this, we see that makes sense, because moving from here to there, we first got to move negative X direction, positive Y direction, and then positive Z direction to get to point B. We can now calculate the magnitude of B by just taking minus 40 squared plus 80 squared plus minus 30 squared. Oh, this was minus minus. This is a plus right here. Plus 30 squared. Square root of all that, that's the magnitude. Now the unit vector from A to B is simply minus 40 over that AB dimension, I, plus 80 over AB, whatever that is, in the J, plus 30 over AB in the K. And actually, the unit vector for the force, the tension force, is actually going to just be the same thing. It's just going to be the magnitude of the tension times that lambda AB. You got that? So that's how we can get the components. This will be the component of the X. This will be the component of the Y. This will be the component of the Z. And then once we have that, we can say, well, cosine of theta X is equal to this. And we can solve for theta X and so on for theta Y, theta Z. Let's see how that works. We're going to lay this out accordingly. This is our strategy and approach. and then we solve for AB in the same way we talked about, like that. Got it? The force then is just the magnitude of the force 2,500 times that unit vector. And we use this line segment, since the force has to align along that wire, we use that line segment to give us the direction we needed. Now this little word about nomenclature here, this is just warning us. We're using this terminology AB. I like this terminology. We're talking about a vector going from A to B, so I call it AB because we're moving from A to B. A lot of other books, especially when we get into relative motion and stuff, they'll use the terminology that that position vector is B from A, and they'll use that, which means going to B, moving from A. To me, that's less intuitive. I like this a lot better, and that's what I recommend. But this, you need to understand that because many books will use that terminology, and sometimes they will intersperse the different methods of talking about it. Okay? All right. So continuing on, we then can go and calculate our direction cosines by just taking that x component over and just doing the arc sine of that dx over x over d, dy over d, and dz over d. Got it? Okay. This is just asking us to evaluate, well, if we already know this force FAB, can we quickly determine what the force is moving from B to A acting on point B? Well, since that wire is in tension, that's got to just be the negative. So we can just take the FAB force and just take the negative of all components, and that will be our FBA force. Equal and opposite pairs. It goes back to that idea from Newton's laws. Okay? All right. So often, though, it won't be quite that simple. What we're going to end up having to do is impose equilibrium. This is more commonly a more complicated problem. We would see something like this here, where we see, okay, we've got a similar system with some things being restrained by some wires, but we may be given some force P. In this particular case, it looks like it's acting in the x direction, and we need to calculate the reactions, either the tension in the wires or the reactions at these points. If we want to know what the tension in the wires are, what we're going to have to do is first find the locations of point A, point B, point C, point D, and point O. So A, we can see, is at 0, 56, 0. B is at, we can calculate the position of B, the x position from this angle, right? And we would need this position. Let's say we know what this dimension is and this dimension is. We can calculate the positions of these other points. Actually, we're going to need a little more information on this particular problem. And then what we're going to do is we would say, all right, we would could take a free body diagram of point A, where we're going to have this point, this force P. We're going to have this force F, or tension, from A to C. We're going to have this force tension from A to B. We're going to have this force tension from A to D. So what we're going to do is use the endpoints. We'll calculate the directed line segment AB by taking this point B minus point A C, which is C minus A D, which is D minus A, and AO, or OA, which is O minus, or A minus O. This would give us the four vectors I, J, and K. We then calculate the length, and we can calculate the unit vector by taking the IJK divided by the total length. We get the unit vector of each of those. The tension in this first cable, TAB, is just the magnitude of TAB times the unit vector from A to B. The magnitude of this vector here, or this vector, is just the magnitude of AC, oops, that's not a vector, times the lambda AC, and so on. We then can sum our forces in the x direction. They have to be equal to 0. So we're taking the force in the x direction. We call this x. We then have the x component, T of AB in the x, plus T of AC in the x, plus T of AD in the x, plus this px equals 0. We write a similar equation, summing forces in the y. This is imposing equilibrium, and summing forces in the z. We're going to get 3 equations, and then we can solve this for any unknowns. You'll notice we have 4 potential unknowns. We have the tension in this cable, and this cable, and the force, the compressive force. Well, looks like I forgot to mark that. This is the POA, from O to A, the compressive force in that member. What we're going to see then, we've got 1, 2, 3, 4 potential unknowns. So we're going to need to be given, say, P and 1 tension. And that will allow us, we can use these 3 equations to solve for the other 3 unknowns. Or we could be given the 3 wire tensions, or 2 of them, and calculate all of our unknowns. That's how we're going to solve that kind of problem. Okay? If we run into a problem like this one, this is similar. In this particular case, we would note that we're going to calculate the line segments from here to here, so we can get the direction, the full force here. All we need is the tension in this, and the line segment from B to G, that's our other one. And then we can see that and this thing can have reactions in 3 dimensions, right? And same thing here. And now we can use that information to solve. Sometimes what they'll do is right here they'll put, say, an eye bolt, and they'll run the cable through the eye bolt. If that were the case, then these 2 tensions in BH and BG would be identical. But if it's tied onto the part, then they aren't necessarily identical. They could be different. So you'll need to read the problem statement carefully, define your endpoints for any vectors, like this tension force, force here and here. And we can also use sum of moments to solve this, because if we sum our moments here, we're going to get a moment acting downward here, moment acting upward here, moment acting upward here. We're actually not ready to do that yet. Right now we're just dealing with a force system, so we just be dealing with these vectors. It's critical that we master identifying the forces along these vectors using these principles now, because if we don't master this now, we will later come back as we build more knowledge and we won't be able to do those kinds of problems. Here's another kind of problem. In this particular case, this is kind of similar. In this case, we can see, you're probably getting a little better now. We can see we're going to have a force. This can have a tension force going this way, a tension force going this way. We can use AC in order to find that tension AC direction. We can use AB to define this tension in the AB direction. And we also have this rod, which could be, and since it's pinned here, it can only have a load along its end, so it can be either tension or compression. So we could draw a free body diagram of point A. We have this TAB. We have this this is AB. This one over here is AC. And then we also have this potential compression P from O to A. Those are all, and then we also have the force P. You can see that P is the magnitude of P in the negative J direction. We see that POA, that guy, POA the vector, is actually going to be whatever the magnitude of that is times I, because it's along the x-axis. And these other two, we can use point C minus A for this unit vector and point B minus A for this unit vector. And then we take whatever that tension is in each times its unit vector, and that gives us the fully defined vector. Okay? So that is the kinds of problems that we can solve using the direction cosines and using these unit vectors. Okay? I'm actually going to back up and look at another set of problems that actually we should have probably presented last lecture because they're planar problems. This is another classification of problem. We have these pulleys. The keys to these, and often what they'll do is ask, what is the tension in the rope? The way to solve this is with a systematic set of cuts. So what we do is we say, well, if this crate has a force W, right, acting down, well, all we need to do to find the tension in the wire. Remember, what we're assuming with these, anytime we see these cables, these pulleys, we're assuming that this is a frictionless pulley. If the pulley is frictionless, that means the tension of any rope going over it has to be the same. It doesn't change moving across it. If there was tension in the pulley, then you could pull on it on one side, you have less tension on the other side because the pulley reacts some of it. But if that's frictionless, then that tension will not change. So all we have to do is just cut this off and replace whatever we cut with a force, and we can sum our forces in the y direction. That's going to be positive equals 0, right? Which means 2 times t minus w equals 0. And in this case, we find t equals w over 2. And we did that by cutting this and replacing what we cut off with the forces. Got that? Let's look at another one. Here's another pulley system. Now what we can do is say, okay, we'll just cut this here. And once again, we see by summing our vertical forces that t equals w over 2. If we cut this one, now we're assuming that this force is actually vertical and not off at an angle. If we cut through here, we see we have to cut through 3 cables. So now if we sum our forces in the y direction, calling that positive, we're going to have 3t minus w equals 0. And in this case, t equals w over 3. See that? Let's erase this, and we got one more to look at. Let's say we have this dude. All we got to do is say, okay, first let's just say, or let's continue this wire up more. Whoops. Let's continue this wire up a bit more and then put the tension. So now we can cut it through here, and we find out we have 1, 2, 3, 4 wires that we needed to cut, all with T. So when we sum our forces in the y direction, we find 4t minus w equals 0, and t equals w over 4. So these problems are rooted in finding the point values, get the line segments, turn that into a unit vector, noting that the forces, the vector forces, are just the magnitudes times the unit vectors. And then summing our forces in the x equals 0, summing our forces in the y equals 0, summing our forces in the z equals 0. And the reason we're imposing 0 is because we're in static equilibrium, which means we're not accelerating the part. Got that? Okay. So this, you're going to want, it's going to be easy if you're in the class to just solve your homework, kind of half understand, and then move on. However, you're going to want to rewatch this video and practice these problems until you've got it. Actually, I don't have enough problems in this video, so stay tuned. I'll be trying to add some more example problems for you in the future once I get the rest of my videos uploaded. If you have a copy of Beer and Johnson or Hibbler or Merriam and Craig or any other undergraduate statics text, they will typically have a few example problems worked in detail following these approaches, and often they'll have problems in the book that will have answers in the back that you can also practice on and check your work. It's really important you understand these concepts because these concepts will continue to be used and will be the foundation for some things we're going to do later. And if you don't master this now, that will undermine any chance of you doing that later work. Okay? So, study the video, practice the problems, look around for a few more problems, or stay tuned for additional worked out problems here Good luck. Make sure you master this before you come back to the next video.